Okay, sorry. I had an alarm set to remind myself to pray for somebody at 2 o'clock, and I needed to do that. So anyway, as I was saying, so the calorimeter, we use heat capacity, not specific heat capacity, and heat capacity tells us how an entire object absorbs or releases heat. Okay, so remember, specific heat capacity told us how a pure substance absorbs or releases heat per gram. This tells us how an entire object does it. Okay, so the units are different. Specific heat capacity, remember, was joules per gram per degree Celsius. For heat capacity, it's just joules. It's not per gram, it's for the entire object, so it's just joules per degree Celsius. There's no mass unit here. All right. To calculate heat capacity, we use a similar equation, but a little bit different. Q equals C delta T, and here the C is capitalized. So this isn't specific heat, this is heat capacity. All right, which again is measured in joules degrees Celsius. Our temperature is measured in degrees Celsius, and our heat is measured in joules. So the units all work out. Okay. You can tell heat capacity from specific heat capacity because heat capacity is a capital, denoted with a capital C rather than a lowercase c. Okay, so let's look at an example. Okay, so I'm going to look at example 13.3 on page 401 if you want to follow along. Okay, and our two equations that keep coming up are Q equals MC delta T, or Q equals capital C, heat capacity, delta T. Okay, so these are the two equations at our disposal. Okay, so let's read through example 13.3. We have a 250.0 gram sample of an unknown metal, okay? So mass equals 250.0 grams. And it's heated to 350 degrees Celsius, so its initial temperature is 350 degrees Celsius. It is then dropped into a calorimeter that contains 1,500.0 grams of water. Okay, so now we have the liquid, which we know is water. Okay, and we're given the mass of that as 1,500.0 grams. And it's initially at a temperature of 24.2 degrees Celsius. The water reaches a maximum temp of 31.2. Okay, so your brain, there should be alarms going off in your brain right now. If the liquid reaches a final temperature of 31.2, then that also means the metal reaches a final temperature of 31.2. Because remember, at the end of a calorimetry experiment, the final temperature is the same for the metal, the liquid, and the calorimeter. Okay, if we read the last little part of this example, then it says if the heat capacity of the calorimeter, so now I know information about the calorimeter. If the heat capacity, and this is a capital C, is 1,410 joules per degree Celsius, what is the specific heat capacity of the metal? Okay, so what are some things we can do before we even really get started? We can calculate the difference in temperature here, and that would be the 31.2 minus the 350. So the difference in temperature here would be 318.8 degrees Celsius. We can calculate the difference in temperature here for the water. And if we do that, we have 7.0 degrees Celsius. We also know the specific heat capacity of water. That's our 4.184 joules per gram degree Celsius. And let's see, the calorimeter, we actually know its initial temperature and its final temperature. Remember, the calorimeter in the water, the temperatures are always the same because they're a unit. The liquid is in the calorimeter. So if the initial temperature of the water was 24.2 degrees Celsius, that's what it is for the calorimeter too. If the final temperature of the water was 31.2 degrees Celsius, that's also the final temperature of the calorimeter. And so our delta T's are also the same, 7.0 degrees Celsius. Okay, so we want to find C for the metal. So how do we go about this? Okay, so I'm going to say, let's start with the liquid because we know, again, 3 of the 4 unknowns here. Okay, so if we analyze the liquid first, we have Q equals MC delta T. So we can calculate Q, 1,500 grams times 4.184 joules per gram degree Celsius times our change in temperature is 7.0 degrees Celsius. So the heat gained by the liquid, if we do all that out, is 44,000 joules. Crazy. Okay, then we can look at the calorimeter. Okay, now remember, calorimeter, we're using the capital C. This is not a pure substance, so we can't use specific heat capacity. We only use heat capacity. So we use this equation. So Q equals C delta T. Again, we have both of these values. So C, it told us, was 1,410 joules per degree Celsius, and our change in temperature was 7.0 degrees Celsius. So the heat gained by the calorimeter was, let's see, 9,900 joules. Okay. So remember this equation. The heat lost by the object is equal to the heat gained by the liquid plus the heat gained by the calorimeter. Okay, so we know both of these things now. The heat gained by the liquid is this 44,000 joules. The heat gained by the calorimeter is 9,900 joules. So the total heat gained by the liquid and calorimeter combined is 54,000 joules. Now you have to watch your significant figures here. Remember the rules when you're adding. This is to the thousands, this is to the hundreds. The thousands is the least precise, so that's what we need to estimate our final value to, the thousands position. Okay. So the total amount of energy or heat gained by the liquid in the calorimeter is 54,000 joules. Well, where did that heat come from? It came from the hot metal. So the metal must have lost 54,000 joules of heat or energy. Okay? So knowing this, we can now analyze the metal. Okay? And we're going to use Q equals MC delta T. We're going to rearrange this and solve for T. That equals Q over M delta T. Well, we know our Q is minus 54,000 joules. It lost 54,000 joules of energy or joules of heat. Its mass is 250.0 grams. And the change in its temperature was minus 318.8 degrees Celsius. Okay, so if we do this all out in our calculator, we should end up with an answer of 0.68 joules per gram degrees Celsius. Okay, I need two significant figures because this 54,000 only had two. Notice that my minus signs cancel out. Okay, so this is my final answer. Okay, so I think the key to solving these types of problems is to recognize what we're talking about. For me, it's easier to list them in columns or something similar to this. We had the metal, we had the liquid, we had the calorimeter, and then list everything we know for all of them. Then look at the data that you know and figure out which one you know the most about and what you can use to start with. Well, I recognized for the liquid, I knew everything but Q, so I could solve for Q. Okay, and I determined that Q was 44,000 joules. Same thing for the calorimeter. Okay, I knew C, capital C, and I knew delta T. So again, I could solve for Q. And that was my 990, or I'm sorry, 9,900 joules. Then I knew that whatever these two as a unit gained, whatever heat they gained, the metal must have lost. So I could add these two heats together, and that's how much the metal lost. Then suddenly, by knowing this variable, I had 3 of the 4 unknowns, and I could analyze the metal. Okay, so we're moving away from calorimeters a little bit now onto a new subject called latent heat. Okay, so we've talked about this before. There's times when heat or energy is added to or taken away from an object, but the temperature doesn't really change. Think in your mind, when is heat added or taken away and the temperature doesn't change? If you remember, it's when something is going through a phase change. So if you look at the graph on page 402, we've looked at graphs like this before during the melting and vaporizing periods. Okay, it's a graph that looks something like this. Okay, during these melting and vaporizing period, the temperature, so this is temp along here, and this is heat. So we're adding heat, the temperature is going up, and then when it enters a phase change, the temperature remains constant, even though our heat is still increasing. Until it's all melted, then the temperature goes up again, until it hits a new phase change, which is vaporizing. Then the temperature remains constant, even though we're still adding heat, until everything is vaporized. Okay, so we've looked at graphs like this before. So now we're going to talk about how all this relates to specific heat and everything that we're talking about. Now we were going to do, well here in this case, all the energy at these two spots during melting and vaporizing, all the energy that's added is going toward the phase change. Okay, it's not increasing the temp. Okay, so all the energy is putting into melting and vaporizing versus raising the temperature. Okay, now I want you to do experiment 13.3 at home. Okay, we were going to do this in class. Instead, you're going to do it at home. It's real simple using household objects. It actually says to use styrofoam cups, but if you don't have styrofoam cups, just coffee mugs will work. I did it at home using coffee mugs. It worked fine. So you can pause the video and go do 13.3 right now, or you can keep watching and do it afterwards. But you will need to do this lab and write a lab report about this. Okay, but it shows you kind of what it illustrates this in real life. Okay, so the amount of heat used in a phase change is what we call latent heat. So it's the amount of heat used in a phase change. Okay, so it would be the amount of heat used in this phase right here, or in this phase right here. Okay, there are two types of latent heat. There's a latent heat of fusion and a latent heat of vaporization. Okay, the latent heat of fusion is talking about when a solid is going to a liquid or when a liquid's going to a solid. So it's this phase change from liquid to solid. Either way, solid going to liquid or liquid going to solid. Latent heat of vaporization is a liquid going to a gas or a gas going to a liquid. Okay, and this latent heat of fusion is abbreviated with as an L sub F for fusion, and this is L sub V for vaporization. Okay, so in most problems you'll be given two values for latent heat. Latent heat of fusion, latent heat of vaporization. You need to figure out which one to use based on if it's a phase change between solids and liquids or between liquids and gases. Okay, the units, just so you know, are joules per gram. Okay, and mathematically, we can express all this in an equation of Q equals mL, where Q again is the heat that's being absorbed or released in a phase change. M, of course, is the mass, and L is the latent heat. Again, if we look at the units, this is in joules, mass is in grams, latent heat is in joule per gram. So over on the right side of the calculation, the grams would cancel each other out, and we would be left with joules equals joules, which is what we want. Okay? Now you have to use your brain to figure out, is heat absorbed or released? Okay? This equation won't specifically tell you, but we'll go through examples, but you guys already should intuitively know if heat is being absorbed or released. Okay? If something is going from a solid to a liquid, so for instance, ice to liquid water, if it's moving from a solid to a liquid, heat is being absorbed, right? It needs to absorb heat to go from ice to liquid. On the other hand, if it's going from liquid water and freezing into ice, we're removing heat, so heat is being released. Okay, so you'll have to think through the part of being absorbed or released, but it's not too tough. Okay, so let's look at example 13.4. Okay, I'm on page 404. Okay, we're told water. So we're dealing with water. It has a latent heat of fusion of 334 joules per gram and a latent heat of vaporization of 2,260 joules per gram. And I'm told I have a mass of 150.0 grams of water. And it says if this many grams of water freeze, how much energy is involved in the phase transition? Okay, so I'm starting with liquid and it's moving to solid because it's telling me this is freezing. Okay, so how much energy is required for the phase change? So how much energy does it take for 150 grams of water to change from a liquid to a solid? Well, we have that equation, Q equals mL. So the heat, or the energy, equals the mass times the latent heat. Okay, in our case, which of the latent heat do we have to use? It's going from a liquid to a solid. So is that latent heat of fusion or vaporization? Well, between liquids and solids, that's fusion. Okay, so we simply take the 150.0 grams. We use our value for latent heat of fusion, 334 joules per gram. And if we do the math out, let's see, I have this on my paper somewhere, 50,100 joules, because you can see that the grams cancel out. Okay, so it takes 50,100 joules of energy for liquid water to change to ice, for 150.0 grams of liquid water to change to ice. Now, the final part of the question then is this energy absorbed or released? Okay, so put your thinking cap on. It's changing from liquid, so from what we normally just call water, to ice. Are we absorbing energy or releasing energy? We're releasing energy. We're getting rid of energy within the molecules. We're slowing them down. So we're removing energy so they can become ice. Okay, the heat is going away. Okay, we're getting to the end, guys. We're getting to the end. So if you need a break, pause the video, come back. This is kind of one nice part about having it on video, is you can take a break when you want. We're going to walk through another example. 13.5. It begins on page 405. Okay. Let's just read through this one to start with. We have 125.0 gram ice cube. Okay. And it starts out at a temperature of minus 8.7 degrees Celsius. At 1 atmosphere, ATM, how much energy would it take to turn all the water in that ice cube to vapor? Okay, so how much energy to take all the water in the ice and change it to vapor? Okay, how much energy to go from all of ice to all water vapor? Okay, it gives us some more information. Let's just jot down. The specific heat capacity of the ice is 2.093 joules per gram degrees Celsius. The latent heat of fusion is 334 joules. The latent heat of vaporization is 2,260 joules per degree Celsius. Sorry, this is joules degrees Celsius. Okay. All right, now we need to think through this. So this process of going from ice to water vapor actually takes 4 different steps, okay? So let's think of what those are. The first step is the heat required to get the ice to its melting point. Okay. The second step is the heat required to actually melt the ice. Melt the ice. The third step is the heat required to get, now we have liquid water. So the liquid to the vaporization point. And the fourth step is the heat required to vaporize the liquid. Okay, so if we think of our heat graph here, here's our 4 steps. Step 1 is the heat required just to get the ice cube up to the melting point. Okay, step 2 then is the heat required here as the ice is melting. Step 3 is taking that melted ice, so now it's just water, and raising the temperature up to the vaporization point. And then step 4 is the energy or heat required to vaporize the water. Okay, so we have to look at each step along the way and figure out how much heat or energy is required at each of these steps. Then we add all those together and we know the total heat or energy required to change the block of ice into water vapor. Okay, so let's start with step 1. Okay, so this is just raising the temperature. So the ice is going from -8.7 degrees Celsius to 0 degrees Celsius, okay? So our change in temperature, well, so actually we want to write that the other way because our final temperature is 0. And then we subtract the initial temperature, so a minus times a minus is actually a plus, so our change in temperature we end up with is 8.7 degrees Celsius. So this is our final, this is our initial, so we're going to take our final, subtract the initial, so we're subtracting a minus, which makes it positive, so our change in temperature then is 8.7 degrees Celsius, which makes sense. We're heating at 8.7 degrees Celsius, right? Okay, so now we can calculate the energy required here. So we have MC delta T. So we have 125.0 grams. C for the ice, it tells us is 2.093 joules per gram degrees Celsius. Our change in temperature is 8.7 degrees Celsius. So our energy at this point is 2,300 joules. Okay, so just for this first step here, raising the temperature to the melting point took 2,300 joules of energy. Okay, now we need to look at the latent heat while the ice is melting. Okay, so the energy required to melt the ice then is just mL. Okay, and which L are we going to use? Fusion or vaporization? Well, remember, we're at ice, it's melting here. So we're at ice going to solid, okay? So that's gonna be latent energy of fusion. So our mass didn't change. We still have 125.0 grams. Latent energy of fusion is 334 joules per degree Celsius. So the energy required for step 2 is 41,800 joules. Okay, let's look at step 3. So now our initial temperature is 0, right? It's all melted. It melts at temperature equal to 0, and we are heating that up until it reaches the boiling point or the vaporization point. So our final temperature here is going to be 100. So the change in temperature is 100 minus 0, which is 100 degrees Celsius. Okay. So here we just do exactly what we did in step 1. Okay, so Q equals MC delta T. Again, the mass hasn't changed. So 125 grams. C, now here we have water. So we know our specific heat capacity for water is 4.184 joules per gram degrees Celsius. And we know our change in temperature is 100 degrees Celsius because we've raised it from 0 to 100 degrees. Okay, so our grams cancel out, our degrees Celsius cancel out, and if we do all this, we end up with 52,300 joules. Okay, and then our last step, so now we're here, we need to calculate how much energy it takes for the liquid water to vaporize. So we use Q times ml. Now it's latent heat of vaporization because we have a liquid turning into a vapor. Again, the mass doesn't change. Latent heat of vaporization is 2,260 joules per degree joules per degree Celsius. Hold on. This is not joules per degree Celsius, this is joules per gram. Sorry, folks. My units weren't working out. Because now here my grams cancel out, here my grams cancel out. Sorry about that. And if we do this math, we get 283,000 joules. Okay? So the total energy it takes is each of these pieces added together. So to raise the temperature to the melting point, it took 2,300 joules. Okay, to melt the ice, it took 41,800 joules. To raise the temperature to the vaporization point, it took 52,300 joules. And then to vaporize the liquid, it took 283,000 joules. Okay, so if you add all those together, you should get 379,000 joules. Again, you have to look at significant figures when adding. The least precise is this last one that's only measured to the thousands, so we can only put our answer to the thousands. Okay, so we walked through each leg of this, raising the temperature, the melting process, raising the temperature, the vaporization process. And we calculated the energy of each of these and then added those 4 energies together to get the total energy. So a lot of steps, but really only step 2 and 4 are new. Step 1 and 3, you already knew from before. Okay, the very last section then is it talks about heat associated with chemical reactions. So there is heat and energy associated with chemical reactions. So some reactions release energy. And an easy example of this is combustion. It's easy to tell this kind of reaction releases energy because we can feel the heat of combustion. It's releasing energy or releasing heat. These kind of reactions are called exothermic reactions. Okay, exo, I remember it as exo is like exiting, thermic is heat, so it's heat exiting. Okay, so these type of reactions give off heat. Okay, some reactions absorb energy. And I'm going to ask you to watch a video that shows a really cool reaction that's absorbing energy. Okay, and these kind of reactions are called endothermic reactions. Okay, endo is kind of like entering, so the heat is entering, heat entering reactions. Okay, there's two more things we need to talk about. Hopefully you've talked about these two terms in other classes, but there's kinetic energy and potential energy. If you take physics next year, we'll talk about these a lot, okay? Kinetic energy is energy in motion. Potential energy is stored up energy, okay? So the thing to understand is within chemical bonds, there's stored energy or potential energy. Okay? So in chemistry, the kinetic energy is the energies that's related to In chemistry, kinetic energy is the energy that's released or absorbed when those bonds are redistributed in a chemical reaction, okay? So in an exothermic reaction, the potential energy in the chemical bonds is converted to kinetic energy. In an endothermic reaction, the kinetic energy is absorbed and becomes potential energy, okay? So there's a couple videos that I'm going to ask you to watch that will help explain this further, okay? But one thing to remember is that in chemical bonds, there's stored potential energy, and then as a reaction goes, that energy converts. If it's an exothermic reaction, potential energy is going to become kinetic energy. If it's an endothermic reaction, the overall reaction actually absorbs kinetic energy from the environment to produce even more potential energy. Okay, and that's what the whole next chapter is about too. So we're just starting to touch on it here. Okay, so that's all the new material. So on Google Classroom, you will see your homework posted. You need to read from page 400 through the end of the chapter, do the comprehension checks, watch the videos, do the experiment 13.3, write a lab report for 13.3, and then do your review questions 1 through 23. And I'll explain all this on Google Classroom, but by Monday morning, March 30th, I need to have your comprehension checks, your lab report, and your review questions emailed to me in the form. So I should receive 3 PDFs. 1 PDF with your comprehension checks, 1 PDF with your lab report, and 1 PDF with your review questions. So I hope all that makes sense. If you have any questions, post them out to Google Classroom. hopefully this went okay. If you don't like this format, let me know. We can try something different or switch it up, but hopefully this will work. Hope you guys have a good week. I miss you all, and I hope you're staying well and safe.